My name's Michael Cox, and I chose texture compression as my project, which I will be honest, may have been a mistake. This is well, I should be honest and say it's my third attempt. My second attempt was only 1 minute and ended prematurely because I'm just stupid. My first attempt was I was even more stupid and had my microphone muted for over 30 minutes while I explained this whole thing, only to realize right at the end, as I was actually finally showing the code, um, that I was muted the entire time. And so here I am, once again, hoping to explain all of this. And so I will start in the same place I started. Um, and that is by establishing the distinction between a texture and an image. For me, when I first started this project, I did not know what the difference between a texture and an image really was. I had a feeling there was an innate difference, but I didn't know what it was. And to be honest, I thought it was far more complex than it was. The texture really is just an image, and the only thing that makes it different than an image is how is it compressed. That's really it. Because an image, just like a texture, doesn't have to be compressed. It can just be raw, uncompressed RGBA data. Um, it doesn't have to be compressed, but and the thing is if it's an uncompressed texture versus an uncompressed image, then they really aren't any different. They are the same thing at that point. That's a bitmap, BMP. But it's when we start talking about compression that there becomes a distinction between an image and a texture, because an image, we all know popular image compression types like the oh god, I don't know how people say this anymore. I say GIF, some people say GIF. I don't care. I'm going to say GIF for the rest of my life, and I don't care if that's wrong. Um, or PNGs, or JPEGs. Um, those are common, well-known, popular image compression methods. And what they do, I don't know the algorithm behind how they do it, but I do know that what they do is they compress the entire file in one go. And all of the RPGA data is compressed in one go, and so it's all decompressed in one go as well. You have to decompress the entire thing, otherwise it won't decompress correctly. Versus what textures do is what they call block compression. Um, what that is right here. This is an algorithm that does block compression. As you can see over here, there's actually quite a lot of them in this library, and I suppose I should introduce what this library is. This library is called Compressonator. It's by GPU Open Tools, which is actually, I believe that's AMD. It's right here. See, software developer at AMD. Excuse me. Ooh, excuse me. I'm so sorry about that. Mm. This library was built by people at AMD, um, and it includes a lot of compression algorithms and a lot of block compression algorithms. The DXT family of algorithms, which they work, they're DirectX based. They're meant specifically. They're designed specifically to work best. So they don't just work with DirectX's API for graphics processing, but The good, really good ones are also the BCN block compression algorithms, and both the DXT and BCN block compression algorithms fall under what is called the S3TC family of texture compression algorithms. That's what I call it anyway. They're technically all classified as S3TC or S3TC based or whatever. And I believe that's because S3TC or S3 was the first block compression based algorithm for texture rendering in games. And that's sort of why they get that name. I believe, at least. I can't exactly remember. Um, I know that. Let's see, which one is it? This one here. This here is an excellent resource to read up on for the BCN block compression algorithms by Nathan Reed. It's fantastic. Uh, I suggest reading it for yourself, but especially because he'll do a lot better a job of explaining things than I probably ever could. But to get back to it, the way that this algorithm works, when it goes to compress the data, it separates the caller data into 4 bytes by 4 bytes blocks of caller data that are 128 bits long. And well, I guess I should say it's 4 bytes with 4 bytes if it's 128 bits, because that math doesn't add up. I guess it could. Was that? Well, yeah, I don't know. Yeah, that math wouldn't add up. But it's a 4 by 4 block of um, where it's a 4 by 4 block of pixels, and there's a these block compression algorithms work best with images that have gradient color changes. So that when there's not a lot of hard color shifts, and that's because of the way that the color data is actually compressed inside of this 4 by 4 block. What it does is it picks a high and a low kind of bound color within that block, and then it uses 1 byte for the high color and 1 byte for the low color, and then it uses the remaining 6 bytes or whatever, the remaining bits that are left over to store the rest of the colors that are in that pixel, which are in that pixel, that are in that block of pixels, and it actually interpolates those colors. And this is why it ends up being a lossy compression algorithm, though, because when you have this type of compression where it instead of compressing each pixel's color data independently, every single pixel having its color data inside of this block compressed, you only have the high color and low color hard compressed, and then the rest of the data, it's some type of 3 byte number that can be used in reference to the high and low bytes to sort of gauge a range of about how far they are from that value. So basically what it does is it interpolates those in between values. Um, and so you can get some rounding error with that, where maybe one of your actual values in your image is maybe one of your pixels in your image inside of this block that we're talking about, this hypothetical block is being compressed. Maybe one of those pixels has a red channel that has a value of 198, and the block compression interpolates it to 196. So you actually lose a little bit of color accuracy there, but it's such a small loss that it's imperceptible to the human eye, and it's therefore within the range of I guess you could say it's within tolerance, right? Because, it's impossible to have this type of block compression for textures and have it be entirely lossless. And the reason that we encode this in blocks, the reason we compress it in blocks instead of compressing the whole texture at once is because of the limitations of GPU memory, as well as because of the fact that when you render a texture to the screen, you may not want to render the whole thing at one time. You may only want to render a third of it, half of it, a quarter of it, three-quarters of it, but not the whole thing. So you don't want to have to send, if you're only looking at 10% of a texture because it's hanging off of the corner of your screen in a video game, you don't want to have to send 100% of that texture's data to the GPU's incredibly limited VRAM to load only 10% of that texture. You only want to send the data that's actually going to be rendered to the screen to the GPU. You don't want to send it extra crap that it's not going to need right away, because then you end up loading the VRAM down with, well, stuff that it may not ever use. What if the player never looks over at the other 90% of that texture? Well, now you've got it sitting in your VRAM waiting to be rendered, but it's never going to get rendered because it's never going to get looked at, so now it's just wasting memory, right? And maybe eventually the memory will get repurposed for another texture, sure, but until that happens, you've got this texture loaded into memory, and that could impact the performance of your game when it's trying to load in other textures, because it may not want to overwrite that texture since it hasn't been rendered yet. There may be some condition where it's like, let's try to use up all of our other memory first before we overwrite anything. And that can, well, I mean, that can really bottleneck your performance. You just don't want that. And because of because you want to have that random access to memory, you don't want to have to pull the whole image. You want to be able to pull, well, essentially a random amount of it. If you need 80% of it, starting from 20% of the way into the file, you don't want to have to start at the very beginning, at the entry point of the file, in order to decompress the portion that you need, the way that you would with an image. Because with an image, in order to decompress it, you have to start from the area that the compression algorithm starts at. So if the compression algorithm started on line 1 and ended on the final line of the color data, then you have to decompress in the same way. So when you compress by blocks, you can decompress by blocks. So it's bite-sized compression and bite-sized decompression, basically. This doesn't always save you memory on your CPU. Depending on what compression algorithm you use, it can actually cost memory. I've seen it when I've been messing with this, where I try to compress a PNG of like a gold coin, and the compressed version came out larger in file size. And I was like, well, that's the opposite of compression. But when you think about it, that larger texture would run faster in the GPU because the GPU wouldn't actually need to load all of it. So while it's a larger file on your CPU, it's actually a smaller load on your GPU because the GPU doesn't need to load that whole megabyte. It can load, 100 kilobytes at a time as it needs it. And so if there's 400 kilobytes of that texture it doesn't need, then it doesn't need to load it. And you actually get a performance bump, even though the texture increased in size. At least that's the theory behind it. That's what I think is happening, but I could be wrong about that because there's also the way that these block compression algorithms work. on interpolating the in between colors and the pixel data, that could very well be the reason why you're not able to do that. But this was the resource I used to learn about the endpoints. See, it interpolates the data based on the endpoint values. Um, this is OpenGL stuff. I did try, and I was able to get an image rendered to the screen. I followed along with this video tutorial from this guy. I got 20 out of 31 videos in deep and realized after I got past video 17 that he was never going to talk about texture compression. And so I've spent weeks following along with this only to feel like I kind of wasted my time. But it did help me understand a lot about graphics processing and graphics pipelines, and it also did still help me. It helped me even further understand the difference between a texture and an image. So I won't say that it wasn't worth my time to do all of that. This is where the original name of BCN was. I wish I could just reject cookies. I do. Block truncation coding. Yes, you can see I tried to get AI to do it for me, but yeah, you get a lot of this, and honestly, this doesn't help me at all. It I don't learn from this, so no. I didn't end up using anything from any AI during this. I stuck primarily to APIs and libraries that are well documented, such as OpenGL and this Compressonator library, and stb image.h, which is apparently a very popular C file that just makes its way around, that's meant to read images of different formats. What's to talk about next? So we discussed the difference between a texture and an image. And textures don't just split things up by blocks, though. They can also split things up by channels and by like type of information that that channel holds. So while it's typical that it's RGBA data, the RGBA data can actually be interpreted to represent things like lighting. So the brighter, you can use a grayscale image, and the brighter a color is, the more lighting is applied to that pixel, and the darker, the less lighting. You could have a normal map which uses a lot of blue to represent height, the height of something, and some of these maps are not very good for compression algorithms such as DXT because of the fact they work off of gradient color changes. So you do have some different block compression algorithms that don't work off of, that work better with images that have more hard color changes rather than gradient changes. But there are a lot of different types of maps that can be made to represent an image, and the various different types of data about that image. And the RPG data can be used and interpreted in different ways to sort of combine those together. Say, for example, you could, I guess, theoretically dump all of this data into the same image, right? You could have just a really large channel that has all of the lighting values attached to each color. So if you want the red to be, highly saturated, like that could be attached to the red channel somehow. At least I imagine it could be. Um, You wouldn't want to send all of that to the GPU for the same reason you wouldn't want to send the entire color image data, because you may not be using all of it. You may not ever use all of it. I think, for example, when you're in a video game and you're a certain distance away from, I don't know, that rock mountain in Skyrim, it looks like mud, right? It's real. I don't know how to explain it, but it looks like if it was a real thing, it would be really squishy. Until you get really close to it. And then when you get really close to it, all these details start popping in, and all these little fine, small little textures start popping in on top of it, right? That's because when you were further away, it sent the data for the larger stuff, but the smaller things, like what kind of map would be best for this? Your roughness map and your metallic maps and stuff like that, or your height displacement map, you may not want all of that data to render, especially if you're really far away and it wouldn't be perceptible to the human eye anyway. Because you end up with the same problem. You're loading down the memory of the GPU. The GPU does not have a lot of memory. All it's got is its VRAM, so you don't want to put things in there that do not need to be in there. You only want to send into the GPU the data that it's going to need, either right now or in the very near future. That is the reason why it's so important to compress textures, so there isn't such a heavy load on the GPU. It isn't entirely just about reducing the footprint on the CPU. So we discussed random access as well. Um, Now these compression algorithms, they're not perfect. They don't preserve 100% of the image's data, and you'll see that here in a moment when I actually get around to. I want to preface everything before I do it and discuss everything. I have a write up here that I made, that I'm following here on a second monitor, so it doesn't get in the way of my code, at least. It's a little markdown. It's got all of the things, basically all my notes and everything. Um, just to show that real quick. Show that this isn't entirely off the cuff. I'm quite bad about doing things off the cuff. Um, it's not like this is scripted, and I'm not really reading this. I'm just reading the large bullet points and then saying what I can remember. But there is at least some structure to this. But like I was saying, these compression algorithms are not perfect. They're what is known as lossy compression algorithms. You have lossless, which is what something like PNG is. PNG is considered a lossless image compression algorithm because a compressed PNG will have the same exact um, data. You can restore the compressed PNG back to the same exact state that it was originally in prior to compression. But with these block compression algorithms like this, as I mentioned earlier about the interpolation, how it's possible that you could have a RGB, you could have a red channel in one of your pixels that has a value of 198, and the block compression algorithm interpolates its value to actually be 196. That's a loss. That's a loss of 2 bits of accuracy right there. And it's imperceptible to the human eye, but if you were to compress that and decompress and compress and decompress and compress and decompress it over and over and over and over again, you might end up degenerating the image, if that makes sense. You could end up in this situation where you lose a lot of the original data. Sort of like, feeding AI its own info will training AI on AI data that generates the AI over time. It's the same thing here. If you compressed and decompress these algorithms, an image or a texture over and over using these algorithms, it's possible that the image could eventually degrade and no longer be recognizable when compared to the original. Though the amount of loss is very minimal, and I imagine that something like that would be really rare. And it's also possible that a lot of these algorithms may also do something to sort of compensate for that and to prevent it in some way. Um, yeah, this is an important thing to talk about as well. Okay. Now, after I started to get a little bit more of a clear image in my head about the difference between an image and a texture, I started to ask myself, well, how does a computer even know that a file is an image? And that's when I started thinking, well, oh, duh, it's the file extension. But that's faulty thinking. And, it's quite common. I imagine it's a quite common misconception that most people in today's world have is that a file's type or format is denoted by its file extension. So if I go into my file tree here, I go and I hit new text document and I delete everything and I do hello.pdf. Yeah, it treats it like it thinks it's a PDF. But if I open it, I get an error saying it could not be opened because it's either not a supported file type or because the file has been damaged. The reason for that is because, and I'm sure, you're a professor, Professor Bo, a professor in this class. I'm sure he already knows this, but file types, files format is not determined by its extension. The extension exists so we as human beings can determine what a file's type is. But the extension does not have to tell you the truth. The extension can be a lie. Now I want to see something. Now, what will happen? Oops. Yeah, I got a little bit of a glimpse of my code there for a second. My recycling bin is on the other monitor. That's okay. Let's open this. You can kind of see where I've been testing it in the past. Now, what if I do this? Let's just restore it. Screw it. And excuse me again. And I go to click on it, and I hit open with, choose another app, Notepad. Just once. Boom. It works. Why? Because internally, this is a .txt. Okay? It is not a PDF. This is a .txt. But the PDF extension is lying. So you have to watch and pay attention because it's not just, oh, I'm just going to change my .png to a .jpeg and now it's a JPEG now. That's not how it works. And I actually learned that when I followed a YouTube tutorial for this as well, and let's see if I can't find it real fast to show what it was. To And you can see everything I've looked up. Open an image in C++. It was this playlist here. I don't even think I got that far into
How's
it.
it going,
Yeah,
everyone?
I just watched the
Today we're
first
going to be starting
Okay, we're not going to play that. Obviously, we're not going to do that. But if you want to check it out, this is, you can see I only watched this first one. But this isn't even it. This is the one that I watched for OpenGL. That's right, because we used STB image in OpenGL. So I used something. Oh, it was this one. No, it was this one. Creating a bitmap image using C++. This was the one
Excellent.
that I watched. I'm very sorry. It took me a minute to find it. This one and this one. Reading a bitmap image. Creating a bitmap image and reading a bitmap image. Those two those two videos were the ones that I watched to and follow along with to create this header file and this class. It's also the video that taught me about file headers. And file headers are actually metadata inside of a file that tells your operating system, hey, this file is of this type. And that's how your operating system determines how to interpret and treat the data that's in that file. So if the metadata says that a file is a text file, then it'll interpret it as a text file. All the characters and anything that comes after it will be treated like actual characters that need to be output to the screen as they appear. But with an image file, I'll show it real quick. If I were to open with text editor, open it anyway in the text editor. This is what an image file looks like in text. And this just goes on and on and on and on. And I'm sure, I don't know, like 2,000 lines almost. 1,400 almost. This is essentially unsigned characters that are 1 byte in length. Right here is the file type, .png. So if I went here and I changed goldcoin.png to goldcoin.jpg and then reopened it in this text editor, this would still say PNG. It would still treat the file like a PNG internally. I would still be able to manipulate and use the file like it was a PNG. Kind of hard to tell where the file header begins and ends in here. I would have assumed that all of this up here is the file header. Actually, maybe just this here is the file header. We got some metadata here. Probably determines the width, and this is typically what you will find in the metadata of a file is of an image file. What type of image is it? And you will also find a lot of this is like the RGBA. Well, actually, this isn't this. Yeah, it's PNG. So a lot of this is the RGBA data. In the PNG compression format. Somewhere up here, the header is the header that tells the operating system how many pixels wide this image is, how many pixels tall it is, or high, up and down, up and down. Its size, which is calculated by multiplying the width in pixels and the pixel width by the pixel height by the amount of channels in your image times the amount of bits per channel. And then I think you divide that by the amount of bytes, and then that gives you the amount in bytes. I think I can't remember the exact formula. Okay, I'm horrible. At 4 o'clock in the morning, my brain does not work correctly. It's soup. I could technically go through here and I could edit some of these and it would change the color data inside of the gold coin image. I'm not going to do that because I could break the whole thing, obviously. I just wanted to do that to show the file header here. That's how that's how your computer knows what a file is and what to do with it. And textures, I would presume all files of all types contain a metadata file header that is similar to the images. It's maybe harder to access than the images ones because to access an image file header, all you have to do is open the image in a text editor. But I would imagine accessing the file header to a text file would be a lot harder. I imagine you would need some sort of special hex editor almost, kind of, to let you edit more so memory address or something like that. But the metadata is usually untouched. You don't compress the metadata of the file. You compress the color data because the color data is what's going to take up the bulk of the file. You're going to have however many channels your image or texture has per pixel. You're going to have that many channels for that many pixels in your image. So if your image is 640 by 480, so you got what is 640 by 480 anyway. 640 by 480. That's how many pixels you have. And then if you have 4 channels per pixel, and if each channel has 8 bits, that's how many bits your 640 by 484 channel 8 bit color depth image is. That's how many bits you're using right there. So that's a lot. Of course, they are just bits, and computers are so good these days. They can load that many. Can load probably hundreds of millions, if not billions, of bits in a matter of seconds. So that's nothing now, but that was a lot back then. And as the images have gotten bigger and bigger, and color depth has increased to up to 32 bits now. Channels can have anywhere from 1 to 32 bits, and it goes in powers of 2. And the higher bits, and I think I explained this earlier, because of the way that the interpolation works. If you have you 8 bits is enough to represent all colors from 0 to 255. But if you have 16 bits, then you could technically have half colors. You could have a color that was somewhere between 250 and 251. So technically, you now have 512 colors. And then, so the same thing would happen with 32 bits, where you now have 1,024 different shades of red that you can have in your 32-bit red channel, for example. I don't know why you would want to have that many shades, to be honest with you. I don't think that many shades of red would be would be perceptible to the human eye. The human eye can't actually perceive that many different colors. I mean, we can perceive a lot of colors, but I don't think that. I, I don't know if 32-bit is too much necessarily, that human beings can't perceive it. But I would imagine that it's not too far off from the level where we get diminishing returns on perception, because now we're trying to render shades that the human eye just doesn't perceive anyway in the first place. So you don't want to, after a certain point, having larger channels kind of just becomes not just redundant, but diminishing in its return. It starts to actually backfire and hurt you. But as I said, the file header is untouched. When it's compression, we compress the color data since it's the bulk of. Oh God, excuse me. It's the bulk of the file. It's the bulk of the texture. And as also I said earlier, you compress that by 4x4 blocks of pixels that are 128 bits in length, where you have 2 bytes worth of those of that 4x4 block used to represent a high collar and a low collar, and then the rest of the bits are used 3 bits per pixel between the high collars would be used to interpolate from the high collar and low collar. A close approximation of the original collar in the image. And it does it in blocks, as I said, so that way it's beneficial for random access by the GPU. And as far as how the GPU actually reads these images, that is manufacturer specific, and it's based on the architecture, a lot like how it would be with SSDs and operating systems. It's manufacturer specific, and it's a black box. It's not like I can look inside and look at the way that the architecture and the code of my GPU is, unless I wanted to, I don't know, rip it out of my machine and hack it. And at that point, and probably would just end up breaking it because I don't know, I wouldn't know what I was doing. But another reason that the block compression is so important is, like I said before, so you're not sending data that's not being rendered. You could end up with, I mean, everybody's experienced texture popping. If you've been playing Skyrim and you're walking down the road, you're walking down the brick road, trying to get the winter run or whatever it's called, trying to get to Solitude. How about that? And you know, I don't know, about 50, 100 in-game feet ahead, there's just a big white square in the road where the road should be. And the closer you get to it, the harder your game starts to freaking stutter. And then eventually the road pops in. Like you go to walk on it, and then the game freezes. And then it unfreezes the moment the road pops in. And then you get this weird, like, everything super accelerates, and then it starts to stabilize. That's actually happening because the GPU's memory is full. The VRAM of the GPU is full. It can't accept new textures that are being sent to the CPU to load. The GPU's like, nah, bro, we're full. I can't load that right now. I can't load that into my memory. Hold on. Hold on to it. So it tells a thread, because that's how it works. It works through threads. It tells the thread that's containing that instruction to load this data to wait until it's done rendering everything that it already has loaded in its memory. And so, if that's a lot of things, that could take a lot of time. And then, as soon as that happens, more memory gets, as soon as that data gets rendered, more stuff to render gets sent into, gets loaded into memory. So you get this weird stutter. And you're lucky if that's all that happens. You can get crashes as well, because it may not just it may not be an issue where it doesn't just load the texture. It may not load the mesh, the position data for the texture, the collision, whatever it is. Well, that might be CPU based, but it may not be. You could have this issue where you just fall through the ground, or where you just crash, and that's not fun. And that's why it's important to make sure that your data is your textures are being compressed well, and you're not overloading the GPU with unnecessary texture data, because there's a lot of texture data, especially in these large games. And now, moving on to the part that I know you've waited about 45 minutes for, the code. um so I showed a little bit of this file. This file right here. This has the ability to create a bitmap image. All of this stuff is just initialization. This is setting up the header of how big the file is, the file type, the width and height of the pixel of the width and height of the image in pixels. This right here, this actually just it sets each channel to a random color. Really, is what it's doing. It's just writing to a random color to each channel. No, sorry, not a random. An increasingly gradient color. It's just this creates sort of a gradient circle. Yeah. I had to learn a little bit of CMake to get this to work because, well, I guess I didn't have to. I could have shoved my image file inside of the same folder, had everything in the same folder, but I like having a little bit of file structure. I do not like it when things are just cowboy chaos and you just got 47 different files of 47 different types all shoved into one place and they all go to something different. No, file organization is very important to me, probably more important than home organization. And so let's build this file here. And we're running it should be VS Visual Studio 2022. Let's see, we want to scan I'll select the kits and see which one it was. It was this one right here. Release 2022 release AMD 64 because I'm on the 64 arc. Actually, that may not be it. Nope, that was it. So then we run it. Wow, you actually created the file. Impressive, I guess. Yeah. Ignore my my not offensive at all error messages. Congratulations, you can read. I thought you got to make it fun somehow. At least when you're first starting out and everything is stressful because you don't know what you're doing. All right, so this little program here just creates, like I said, this line here actually is the one that creates the okay, now I know. I see what it's this here sets the size of the channel, right? And this here is what's actually setting the color inside of the channel. This loop here is what's created will create a gradient circle. And and it sends it to my text press, which I will now show you that. This is an entirely separate solution in Visual Studio, an entirely different IDE. And here we use an entirely different method of loading images, one that already has PNG, BMP, GIF, and I've actually never seen PIC, and it has some limited support for JPEG as well. It even has some support for HDR files. This is a quite popular file. It's so popular that you can just Google this header file and find it by itself in a repo. It's essentially a C file for reading images. And I use this to read the bitmap image that our program created. This here is the Compressonator header file that was given to me when I downloaded the API. So these are all of the functions that I am able to call and work with in this API here. It's quite a good number of functions. I tried messing with the compressed texture stuff, but uh, not all of it makes sense to me, and I won't. And since it's like a open source GitHub thing, I won't. It doesn't have the best documentation, but I won't sit here and say that there's no answer to what I was trying to do with that. Maybe I just didn't look hard enough. But from what I can tell, this already is enough. This here was basically started out as just an example of the API that I've basically just co-opted for this. You actually have to send the arguments to stuff through the command line. See, it takes command line arguments, and you can kind of see it gives you an example here of how to run it. So we'll go ahead and do that real quick. Actually, first, before we do that, we need to make sure that our image file is properly generated. And guess what? It was. There it is. This is the gradient that was created by this program here. This little tiny program, OpenCV2. So it is a 24-bit per pixel BGR image. So it's actually backwards. Instead of an RGB, it's a BGR. But that's fine, because that actually is the type of format that OpenGL works in by default. OpenGL would refer to it as RGB, but it's actually BGR. It's confusing. OpenGL is just backwards, at least the implementation that I was using. And that already is a beast, a big monster to try and tackle graphics APIs, considering that each graphics card and graphics card manufacturer is going to have its own API implementation. So OpenGL on NVIDIA cards won't be the same as OpenGL on AMD cards, which won't be the same as OpenGL on Intel cards. Well, I guess really what I should say is something like DirectX can only be used on Windows slash Xbox machines, and Metal can only be used on Mac OS or iOS, stuff like that. You got some GPU manufacturer specific APIs. Then you've got open source APIs like OpenGL that is cross compatible and does work on every GPU manufacturer has an implementation of OpenGL on it that they have on their GPU. So you can use OpenGL on all graphics cards. It's cross compatible, but it may not work exactly the same going from one GPU to another, is what I'm trying to say. And it's because of the fact that GPUs, oh God, excuse me again, they're essentially black boxes. So our image was generated. It's beautiful. It's gorgeous. It's the greatest image I've ever seen in my entire life. I've never seen better. So what happens if we compress it? Okay, that was weird. This whole terminal is ugly and I don't like it. So let's fix that. So we can actually see what's happening here. Okay. So we'll start with BC1, because we have a lot of different methods we can use. B13, that's a vitamin. That sounds like a vitamin. This 0.1 is like the quality of compression of the compressed, it says it right here. Shows how to compress a single image by generating bitmap levels. Bitmaps, I believe I explained that. The way I think of a bitmap is like a stack of images where it starts from the original image and then goes down to 1 pixel. And it tries to represent the original image in those different sizes, all the way down to 1 pixel. I think I showed. No, I haven't showed one yet. That was my first attempt. And starting to get it all mixed together, because this is already almost an hour long. So we can see here compression progress. processed in 2.446 seconds, essentially longer than the first attempt. And if I look at the way that I have this written, the API saves it. Where is the line? Determines where it gets saved at. Right here. Where does it determine the destination file? That's right. Duh. The destination file is one of the arguments in the command line. I'm stupid. So it'll save it. This is where it's loading. This is where it saves. This is the compression format. This is the compression quality. So if I reload this, boom, there's my texture. And as you can see, mostly the same, but it is a different format. It's now 4 bits per pixel. So we've actually lost quite a bit of our original quality. You can even see it when you look at the image. You got these kind of like scan lines here. It's because, again, the block compression interpolates based off of high and low values. And so when you've got lower bits per pixel, you have even larger interpolation errors. So you end up with basically what are essentially larger jumps in color going from block to block. That's why you have these lines like this. So if I were to choose a better compression algorithm that used more bits per pixel, we could get that to go away, and I will show that here in a second. There's something else I was going to do, and I forgot what it was. I want to show the bitmaps. As you can see, as we go down in bitmap, you'll see the quality starts getting worse. You also see the width and the height reducing. See? So now we're at 8x4. Now we're a 4x4. And then we're going to become a 4x4. Okay, so but you can see it shrunk all of our color down to 1 pixel, and then we're going to expand back out. So if for some reason our texture was rendering in 1 pixel on the screen, it would choose this bitmap. Because why would it want to load 640 by 480 pixels when the position of the texture only takes up 1 pixel? It'll just load this bitmap level and use it, which will save a significant amount of memory on the GPU. Bitmaps alone are genius, in my opinion. So let's take a look here. Our original image right here, it is 900 kilobytes in size, and our texture is 200. So yeah, that is compression. It got lots of smaller. It shrunk. Yeah, that is compression. That is good. But can we do better? Or can this do better, I should say. So let's check out BC3. 2.26 is slightly faster. And there it is. Now let's look at our image. And now you can see already compared from BC1 to BC3, those lines aren't as hard or as many. And I'll tell you what else is interesting. The original image here does not have an alpha channel, but these compressed versions do. Which is interesting to me. I think that might be just something of default. And a lot of times that will happen. If an alpha channel is not specified, it'll automatically just assign 1 bit to the alpha channel and just make it 1. Okay. Properties. You close out the terminal and reopen it because I can already tell it's about to look ugly again. Okay, so let's try BC4. 1.932 seconds. We just broke the 2-second barrier. And what about our image? Ah, now you see here what's happened. It's turned into a grayscale image. And that is likely to do with the way that the algorithm itself is designed. It's possible that it's intended to turn this into a grayscale. It's also possible that it read the channels in an order that is not the same as how it's stored in the file. It's also possible that this is actually sort of like a specular map that got generated based on the brightness of the pixels going from left to right. As you can see if we zoom in, you actually have like a gradient smoothing going from black to white. You can see it here too, the original. Now, what about... This is fascinating to me because I haven't tried every single one of these compression algorithms yet. I've tried a good bit of them, but not every single one of them. And this is, I'm not going to sit here and try every single one of them either. I'm going to try this one and then one more after this one. 1.662 seconds. And so let's check out this one. Now this isn't even the same image. Something happened here where it's not even the same image anymore. You could call this lossy for sure. Maybe maybe it's the same issue again. The way that the channels are organized in the file is not the way that the compression algorithm expects them to be. As you can see, this is our original image. And yeah, I don't know why it's like off like that. It's kind of annoying. This is our original image. Kind of, you know, it's kind of like a hue wheel. Like, you know, like a hue selector. I can come up here like, oh, blue, pink. It's what it's kind of like. And then this over here is like, okay, just green to red. So that's interesting to me. Now, I know for a fact which one of these algorithms does it best, but before we check that out, let's check our image sizes. So again, for reference, the original is 900. This one was 200. And then this one, 400. So you can see it got a little bit bigger. Ooh, 200. And then this, 400. Okay. So let's close this. Go back to main. And now let's one last test. We'll do BC7. Now, in my opinion, BC7 is the best one in terms of quality. It is the newest one. 2.495. It is also the slowest, though. If we look at BC7, it's indistinguishable, nigh indistinguishable from the original image. There's no hard line shifts. It does look like we have a couple of artifacts, like here and here. Oh, okay. I didn't know that that was going to happen. Can I undo that? I can. Cool. And here, not there. I don't know if you can see them. I see them. It almost looks like I'm seeing shapes inside of the image that shouldn't be there. If I look at the original image, I don't know, they're there in the original image too. Okay, so never mind. And if you look over here, it reduced our original image from 24 bits per pixel to 8 bits per pixel. And this is essentially exactly the same image. There's a little bit of loss. It moves down ever so slightly every time I close it, reopen it. So like up here, you kind of see how the original image is more blue here. Mm, um, It's hard to tell. If there is any data loss, it's imperceptible to the eye. I want to say that it doesn't look the same, but I literally can't. Because every time I try to find something to point out, think I have, it's like, oh wait, that's no, that's the same. So yeah. And the last thing I wanted to show was a little bit of the OpenGL stuff that I did, but to be honest with you, none of this is really relevant. It is a lot of code, it is a lot of work. That's just a debug folder. I didn't code that. this this process took me through learning how the linker works and learning about the graphics pipeline and stuff, which, like I said earlier, did help me understand a little bit of the distinction between a texture and an image. But as far as this project is concerned, I tried to get one of my compressed texture images to render in OpenGL, but I couldn't figure it out in time. It took me so long just to get to this. I could at least run it and show you what it does, I guess. Wow, my error messages are everywhere. So if I run it, I get a coin rendered to my window. It doesn't even center the coin or anything. It's my little shader code that I wrote that I'm injecting through OpenGL. Uh, but I could never get my own compressed texture to render there. I can render the bitmap image that the first program created. Testimage.bmp. That's an older one, but it renders the same image almost every single time. So if I change goldcoin.png to testimage.bmp and then I re-render it, yeah, it's stretched, it's ugly, it doesn't format the proper aspect ratio, it doesn't center. It's yeah. And if I try to do compressed texture, first off, all of my texture stuff is here. I'd have to change all of this because this works with flat texture, uncompressed textures, and I don't necessarily know how to rewrite it to work with compressed textures. So, unfortunately, my plan to be able to render my compressed texture within OpenGL or Unity fell apart. I guess I could have focused on trying to do it in Unity, but I really wanted to challenge myself with OpenGL, and I guess it didn't pan out the way that I hoped. But at the very least, I was able to get this much. Okay, I am having a little bit of fun. Just one more for the road. Let's see what happens if I do BC6 because I've never done BC6. It's the only one I haven't tried. Ah, that'd probably be why, because BC6 is not supported. There is no such thing. It's probably the same thing with BC2. Probably is no BC2. Oh, there's BC2. So I've never looked at BC2. So let's look at this together. And then yeah. 8 bits per pixel. Honestly, not bad. I mean, it's got the artifacts that the other ones do too, but really not as bad as I was anticipating. Um, that's really it. Thank you for suffering with me for the last hour. I know it's been a long video just to hear me kind of ramble while I sit at my computer and sort of screw around with various programs that I hobbled together from YouTube forums, from internet forums and YouTube tutorials. Uh, so that was my texture compression project. Thank you for listening, and if you made it this far, then you have some incredible patience. And I really applaud you. Alrighty. And now y'all have a nice day and stay safe.